Welcome. This is the second in a series of videos training you to use spreadsheets in physics labs. There are three files available to you. There is a PDF lab write-up where you're given instructions on how to do this laboratory. There is a spreadsheet report template, or just a report template. It's in Word. It's a Word document. And then there is the all-important spreadsheet template. Okay, so in this lab, you are asked to do a few things, and we're just going to run through all of them. So first of all, we're going to do something that we did last week, which is just generate a set of data that are all along a line defined by y equals mx plus b. So let's just choose some numbers for the slope and the y-intercept. Let's leave this random number blank for right now and just generate our x and y data. So our independent variable is going to be, we're going to start with 0. That's kind of funny. I'm going to right click and change the format of that and make it just a general number. Enter 1 here. Select both of them. Click this little handle and then drag down. And that automatically repeats that pattern. So our dependent variable is going to be calculated according to this equation. And it is equal to m, the value m, times the value x plus b. Okay, so let's do a gut check on this. So 0 times 2 is 0 plus b, 3 is in fact 3. Now let's drag this down. Oops, we've got some problems here. What have we done incorrectly? Well, we have used all relative cell references, right? So instead of maintaining the position of m and b, which are only in these fixed cells, we have continued this pattern C5, C6, C6, C7, etc. So that's not what we want. We want to use fixed cell references. That happens a lot. We want to use fixed cell references to lock the cells C5 and C6. So to do that, let's start over. We'll say equals m. And I'm going to fix that by putting dollar signs in front of both the column and the row denotations by pressing F4. I can press F4 and it puts dollar signs in front of there. You can cycle through all of these as well by hitting F4. So we'll just leave it with the dollar signs in front of those, in front of both of them, times x. So this we do want to be a relative cell reference, plus b, which we want to be a fixed cell reference. Enter. Now when I drag this down, it maintains m and b in these positions and we get the correct thing. All right, so let's plot this. I'm going to select an empty cell, go to insert, scatter plot. I'm going to right click, select data, add. The x values are here. The y values are here. And there's our line. Now we can change these values of m and b and automatically update the chart and all of the data and the chart. Put b at 0. Excellent. All right, so we've generated a set of data that are along this line. Now we want to add some fuzziness to this, right? A little bit of experimental noise, because when we actually take measurements, we aren't going to get perfect data. To do that, we're going to use a new function that is called rand_between. So let's just explore this function a little bit. I'm going to say that this cell is equal to rand between -5 and 5. Okay, I'm going to drag this down. So anytime this spreadsheet updates, it gives me some integer between -5 and 5. It is actually inclusive of -5 and 5. Let's see if we can't get one of those. Here we go. So there's a -5. A 5 isn't showing up, but that's fine. So we kind of want a random number that is a little more precise than that, right? Maybe we want it to be between 1 and -1, but we want it to the 10th place. So what we need to do is divide this number by something to get that finer precision. So for example, in this cell, let's just divide it by -10. Or sorry, not -10, just 10. So this should now give us some number between -5 divided by 10, which is -1/2, and +5 divided by 10, which is 1/2. So we have increased the precision of our randomness. So that's what is meant to be done with this cell. I'm going to delete this, and we're going to go ahead and implement our strategy here. Let's just increase this randomness to, let's say it's 100. Or actually in the lab it says it's 50, so let's do 50. And this is equal to, this fuzzy data is going to be whatever's in our y column plus this fuzziness. So that cell plus rand between negative this number and positive this number. Except we want to lock those cell references. So I'm going to select it and press F4. Select this, press F4. Close parentheses, and let's just divide by some number, let's say 10. Okay, I'm going to drag that down. So we see we've added a little bit of fuzziness to this data, a little bit of noise. And we want to plot that and kind of update this live and see how it changes the fuzziness of this data. So I'm going to select this data, right-click, go to Select Data, and now I can edit this series. Now instead of the y data values, instead of these, I want these. So I'm going to select the y values to be a different column and click OK, click OK. And there we go. So now we have added a little bit of noise to this data. Let's try and increase the randomness of this. I'll go to 100. Right? We see that it gets even fuzzier. 200. Right? It's starting to look less and less like a line, even though it originally started out to be a line. So we want to explore and quantify these things, and to do so, we need to use this statistical technique called linear regression. There are two different ways to access this in Excel, and we're going to use both in this course. The first is pretty easy. We just highlight the data on a plot, right-click, add trendline, and it adds a line that kind of approximates where this line, or the line of best fit for this data. If you click on the line, you're given a lot of options over here, and the two that we need to set are the display equation on chart and the display r² value on chart. So that actually gives us the equation. The equation of this line should be y equals 7x plus 0. Let's change it to something maybe a little bit more interesting. How about, or something with a b. And we come pretty close, right? We've got y equals 2.27 plus 0.75. That's actually not that great. Let's decrease the randomness a little bit and see if these numbers don't get closer to their original values. So I'll just make that, say 20. Let's make it 10. The data are getting more and more close to being in a straight line. And we are getting closer and closer to our original slope and y-intercept. Now, the closeness of the line to the data is also quantified in this statistical measure called r². And this is a number that is between 0 and 1. If the randomness is 0, right? If all of the data fall on the line perfectly, the value is 1. And the closer it gets to 0, the less like a line the data are. So yeah, let's just go ahead and put 0 here and see if it gives us 1. Yep, look at that. It gives us back our original equation, and the r² value is 1, or the data perfectly fit on this line. Okay, so let's put a little bit more randomness back in here. Something like that. Of course, we'll go ahead and label the x and y axes. But before I do that, I will point out that sometimes you want to increase or decrease the precision of the numbers in the displayed equation on the chart. So to do that, you select the equation, right-click, go to Format Trendline Label, and here you're given all of the formatting options. So we can decrease the number of decimal places, increase them, put it in scientific notation, whatever you need to do to increase or decrease the precision of these numbers. Okay, so a little bit of chart formatting. Give it some axes titles. This is the x-axis. These are very generic. These will eventually contain real physical data, so they will have units. Units I usually put in square brackets. This unit is dimensionless, right? These don't have any units, so I'm just putting empty brackets there. Again, a little pedantic, but why else are we in school? But to hear from pedants. Is that right? Okay, y-axis, open, close bracket, and there we go. So this is a good plot. The other way to get the m and b data, extract the slope and the y-intercept from a set of data, is to use the linest function. And the linest function is a little bit complicated, but it gives us the slope and the y-intercept in a spreadsheet so we can use it in calculations. The linest function is something called like an array function, and to implement this the way that is easiest or most useful in this course, you select a 3 by 2 grid of empty cells, and now we're going to press equals L-I-N-E-S-T, linest, open parentheses, and it gives it a little context menu there. The known y's, so our y values are our fuzzy y data, comma, the known x's, comma, and then 1 and 1. That just gives some like extended statistics. Now what you absolutely do not want to do here is just press enter. Instead, you need to press Control Shift Enter. That's the way array functions work. Anyway, so that brings up the slope, the y-intercept, and the r-squared value, so we can double check that these are the same. 1.768, 1.768, and 4.404, 4.404, 0.966. Great, so all of those are in order. The other statistics that this function gives you are the uncertainties in these values. So the slope or the y-intercept may have physical meaning, and when you go to report a number, you only, or the value of weight, for example, or a gravitational acceleration constant, or a pressure or a temperature, it always has some uncertainty associated with it. So we only know the value of the slope to this uncertainty. Of course, we can't know, we only know the uncertainty to the tenths place, right, the 0.1 digit. So if we go to report this number, we only report the slope to the tenths digit with appropriate rounding. So I'm going to say that the slope with the associated uncertainty is 1.8, because I rounded 0.7 up to 8, or up to 0.8, plus or minus 0.1. So that is how you would report the slope plus or minus the uncertainty in that slope. Now I think something strange is going to happen here when I press enter. All of the numbers changed. That's because the rand between function calculates, recalculates, it creates a new random number every time you change the spreadsheet in some way. So there's several ways around this. Honestly, for most purposes, this doesn't really matter. But if you want to kind of fix those numbers so these things don't change, I think the only way to really do it is to copy. So Control C, and I'm going to paste here into a new set of cells. I'm going to paste as values. Okay, so now that gave me a fixed. Now these are just individual numbers, and there's no more rand between function in there. So this would be fuzzy y. And then you would plot this, and all of these things would remain static. Okay, so let's just quickly copy these into our report template. I'm going to delete this red part. You're asked to copy all of this information. Let's just do all of this. Control C. Now when I come in here, I'm going to right click and paste as picture. I'm going to right click the copy. Also, you could just Control C that. And I'm going to again right click and paste as picture. As far as formatting is concerned, we're going to make this square and this one also square. And now I can kind of resize these so that they all fit on the same area of the page. I probably made the precision a little bit too high on on these numbers, right? We only know it to 1 decimal place, or to the tenths place. Okay, and that is the first part of this. Just answer these questions, play with the spreadsheet, a little bit more, and you should be good to go. Okay, second activity is measuring absolute zero. Let's increase the size of this a little bit. So these are real values that I took. I could perhaps show you a picture of the vessel in which this data was taken. This was like a sphere of copper that was originally meant for a float, like an industrial float. But I drilled a hole in it and put a valve and a pressure gauge on it. I pulled a vacuum on this sphere and backfilled it with argon at standard temperature pressure. So 1 atmosphere is 25 degrees C. Is that standard temperature? I think it is. And and then you can take a bunch of temperature and pressure data on this. We have a few points. We have the pressure at, I put this in boiling water, so it was almost 100 degrees C, and measured the pressure. I then put it in a water bath that was at 50 degrees C and measured the pressure. Put it in an ice bath, measured the pressure, and finally in a bath of alcohol with ethyl alcohol with some dry ice in it. Dry ice is actually a little bit colder than this. It's like -80, but this is just where I took this data point. So we want to plot this and try and create a model of the behavior of the pressure as the temperature is increased or decreased. We've got 4 data points. All we need to do is just insert a scatter plot, right click, select data, add our x values. This is the independent variable. We controlled the temperature and we measured the pressure in pascals. Okay, and there is our chart. We say this is pressure versus temperature for a spherical container of argon. Not that it being spherical is that important, or even that it's argon. I really don't like these numbers right in the middle, so this is one thing that I like to change. Right click, format axis, labels, low. And while we're at it, let's complete our chart by making sure that we know that temperature in degrees, Celsius is on the horizontal axis. Add chart element, primary vertical, and that the pressure in pascals is on the vertical axis. Okay, now we can analyze this. Let's go ahead and add a trend line. I'm going to right click, add trend line, display equation on chart. Kind of move this up here. Awesome. So now we have an equation that tells us what the pressure is, or the y variable is at any given temperature, which is the x value. So that's why I've put both of these equations here, right? The pressure corresponds to the y value, and the temperature corresponds to the x value. So you can kind of just draw arrows down to each one of these and see which one corresponds to which. But I do want to use those these two values in some calculations. to do that, we actually need to use the linest command in addition to these additional statistics. A lot of additions here. So I'm going to do this gambit of selecting 3 rows by 2 columns, pressing equals, linest, open parentheses. The known y's are the pressure values. The known x's are the temperature values, comma 1, comma 1. You can close the parentheses and then press Control, Shift, Enter. And we can confirm that these are the same numbers, 328.49 and 90141, and the r-square value is the same. So we know the y-intercept, or sorry, let's just go back to the slope, to the tens digit place. So if we were to report this number, the slope in pascals per degree Celsius as 330 plus or minus 30 plus or minus 30. Okay, this would be probably even better to report this in scientific notation, but that is one way to denote that. Okay, but that's not part of this lab. What we do want to do is use these numbers in calculations. So for example, I ask you what the temperature, or I'm sorry, what the pressure of this vessel is at 80 degrees Celsius. So you could, sometimes you're only given a chart, right? You're not given the slope and the y-intercept of this line. You're just given a chart, so you have to interpret this chart to find the data that you want. So let's just do that. We want to know what the pressure is, what is on this axis, at 80 degrees Celsius. So we go to the 80 degrees Celsius mark, follow that up, see where it hits this line, and then go all the way over. So that looks like, I don't know, what, 118,000 pascals, 118 kilopascals. We can do a little bit better with this chart by making it larger, but we can also add some grid lines, some finer grid lines. So we go up to the chart tools. Okay, so if this is a ribbon, the chart tools must be a spool, right? Because a ribbon is on a spool. So the chart tool spool comes up when you click on the chart, and you go to the design ribbon, add chart element, grid lines, and primary minor horizontal, and primary minor vertical. Okay, so that gives us a little bit better resolution. Okay, so now we go to 80, and then we come all the way over here. There are 1, 2, 3, 4, 5 from 100 kilopascals to 120 kilopascals. So 20 kilopascals divided by 5 is 4. So this is going to be 116 kilopascals. So that's our estimate from our graphical analysis of this. Let's do it using these equations to get an even more precise result. So I just need to implement this equation, right? I want to know what the pressure is given this slope, this y-intercept, and this temperature. So I'll say equals m times the temperature plus the y-intercept. We could make these fixed if we wanted to, but we're just doing one calculation, so it doesn't really matter. And there you go. Our graphical result matches pretty well with our analytical result here. Okay, so for question 3, you're asked kind of the inverse, right? We need to rearrange this equation to determine the temperature at some given pressure. So we just do a little bit of algebra and we come up with this equation, and we can find that similarly, we've got this pressure. We're following this equation minus the y-intercept divided by m. So I've done something wrong, right? Right now we're just dividing b by m and not the quantity p by m. So I need to alter this equation a little bit, put some parentheses in here to get the right answer. Okay, so I believe I looked this up for this sphere, right? This sphere here, what the the ultimate pressure, the bursting pressure of this sphere is, and it was around 300 kilopascals. So you know that if you heat with argon in it, if you heat the sphere up to 638 degrees, it will blow up. The last question I leave to you, and it is sort of a philosophical question too, right? What is temperature? Temperature is just the motion of the atoms in a, in this sphere of gas, or the motion of atoms of, any atom. And so what happens to the temperature when the pressure goes to zero? The pressure going to zero just means that nothing is moving, right? So this is that all of the atoms are as still as they can be. So knowing the temperature at which that happens gives you kind of a fundamental thing in the universe, which is absolute zero. So using this data, you can extrapolate what absolute zero is, where this line crosses the x-axis. So anyways, that is about it. I hope you found this useful, and I'm gonna sign off now. Goodbye.